I'm Craig the Geologist, and today I'm coming to you from the Rainbow Mountains here in that beautiful land down under, China. Come join me. The Rainbow Mountains are located in the Zhangye Danxia Geopark near the city of Zhangye in Gansu province. Here in the edge of the Inner Mongolia Gobi Desert area in China. They are, as the name suggests, the Rainbow Mountains, very colorful with reds, yellows, grays, and even greens. Although most of the time when you see pictures on Google or Instagram, things like that, people have photoshopped the colors so dramatically, it looks like it's just AI. It's kind of ridiculous. But this is what they look like to your eye, to a camera without all of those modifications. The geology here is fairly simple. You might think it's real complex because of those colors, but in fact, I can tell you from looking at it, it is all sandstone, siltstone, mudstones, clays, some shales. It's all basically fine-grained sedimentary rocks. Nothing too exotic about that. The colors come from what those sediments are holding on to. Your grays tend to be your clays, tend to be rich in a lot of illite and other clay minerals. Your reds tend to be more your sands. They're holding a lot of iron. The yellow, now I'm not too familiar with the geology of this area, but the yellow I would suspect is probably limonite, which is another iron mineral. Perhaps it's an iron sulfide. I will fact check myself on that later. The red will be from hematite. That's basically rust. So this was deposited in a very iron-rich oceanic environment. And those red layers, that's oxidized iron. And those yellow limonites, I would suspect those were formed in more anoxic environments. But if I'm wrong about that, I will correct myself in the video here in just a moment. I'm only afraid of being wrong insofar as I don't want to misinform you. I'm not embarrassed to admit that I don't know everything. No one does. This is a gorgeous location. 360 degrees. It being China, there's, infrastructure everywhere. So even the World Heritage Site is crisscrossed by power lines and telephone poles, but it's a really beautiful spot here. The Zhangye Rainbow Mountains are a rather busy place. Now, you get that at U.S. national parks too, especially some of our more popular ones. And if you've ever been to Zion National Park, some of this setup will look familiar to you. You can't drive wherever you want to go. You have to take a bus there. And they do that both here and there for crowd management. But if you're looking to find a nice secluded trail without very many people around, you're not going to find that here. You're not going to find that anywhere in China. It's a very populous country. And pretty much any place that you're allowed to go as a tourist, there will already be plenty of other locals going to as well. Oh, and in case you were wondering, the temperature is just over 100 degrees, and it'll remain that way all summer long here. It's a hot location. The black surfaces clinging to the ground here, especially the dirty, like literally dirty, just clinging to the dirt rather than the rocks, remind me a lot of the cryptobiotic soil in the western US. Now, I'm not sure if it's exactly the same, but I suspect, if not exactly the same, it's very, very similar. I'll try to get a close-up of it later, but the authorities here are very sensitive about anybody walking off trail. Cryptobiotic soil is a mixture of things. There's bacteria mixed in, microorganisms, fungi, and especially a lot of lichen. It is its own little microbiome in every square inch of it. It is extremely slow growing. It grows, I don't know the rate of growth. I'll post it in the video in a moment. But it grows very slowly. As I recall, it takes about 100 years for the surface to form. The cryptobiotic soil is extremely important to these desert environments because it holds the dirt in place. In the western US, the cryptobiotic soils were trampled mostly by cattle when herders would herd them out west. And without that cryptobiotic soil to hold the sand in place, massive dust storms kicked up. Played a big role in the Dust Bowl. So we've learned how important those cryptobiotic soils are. Without them, there's massive erosion, massive health problems for everyone who has to breathe that dusty air. So before we move on from this specific overlook, let's take a quick look at the colors we can see from here and understand what they're telling us. We have black cryptobiotic soil clinging to the eroded dirt surfaces. We have beautiful red sands. And they're probably fine grained sands. They're probably not coarse grained. We come over here. We see more of those red sands formed in an oxidizing iron-rich environment, and those yellow limonite sands. And we see those white clay layers there as well. All right, well, I'm at another overlook here, and I'd like to point out some other features that I'll probably explain in a voiceover rather than doing it here because of the wind across the microphone and pre-recorded Chinese safety messages blasting in the background. But pretty awesome stuff right here. Let's take a moment to talk about the shape of these rocks, or more accurately, the larger scale shape of the landforms. And toward that end, I'd like to just pause this video for a moment. What you're seeing in these landforms are these rather triangular shaped blocks. And what it's showing you is the hardness of the rocks. What you're seeing in these incomplete triangles is two distinct slopes, one on the left, one on the right. The one on the left, you'll notice, is fairly consistent between each triangle, we'll call them. And what you're looking at there is called the dip. That is the slope that the rock is coming out of the earth at. In each region, that's going to be a pretty consistent angle, and we're kind of seeing that in this picture. The right side of the slope is the erosional slope, and that's going to vary a little bit depending on how soft the material is and how far the bottom of each valley is. Geologically speaking though, what we're really looking at are resistant rock units and more easily eroded rock units. The left side of those partial triangles, those are your resistant units that are kind of protecting the softer material underneath and allowing those to rise up beneath them. But those softer materials are eroded away. Those harder protective units that are on the left side in this case, those are often referred to as cap rocks. And you can kind of think of them as serving the same function as a protective umbrella over the softer rocks, keeping them from eroding away. On the rare occasions it rains, water falls, strikes the resistant cap rock and runs down that slope on the left, protecting the softer rocks on the right or underside. So these Rainbow Mountains are absolutely beautiful. Great colors, starkly just rising right out of the rocks. You know, it reminds me a lot of the Red Rocks area at the base of the Rockies, running from Denver down through Colorado Springs and even south of there. I gotta say there's a lot of similarities between what we see here and what we see out there. The colors are a little bit more dramatic out here, though not much more so. I've climbed a lot of stairs today. But the question remains, how did this stuff form, right? Like, why is it here? Well, the colors, as we've discussed, come from the minerals in the sands and clays that this is all made of. How did this rock form? This was all probably shallow ocean material. Again, I haven't gotten close up to study it, but based on what I'm seeing from a distance, it's all fine-grained sands, muds, clays, and I see shales out here too. And that tells me this is a shallow ocean environment. The reds are oxidized iron. Those would have formed when there's a lot of iron in the ocean and a lot of oxygen. The yellows, the limonites, those are actually hydrated iron oxides. So there's no sulfur in there, as I mentioned earlier. However, it is associated with sulfur. So those could be units that have more sulfur in them, have turned yellow, as the hematite that's red remineralizes to limonite, which is yellow. We see the blacks in here, which are the cryptobiotic soil. And the whites are the clays, and the clays would have formed in an offshore environment. So your coarser grained sands form closer to shore. The further out in the ocean you get, the finer grain they are until they become clays. Those whites you see, those are the clays. So what you're seeing are changes in sea level through all the striping here. Where your white clays, you have high sea level. And it's hard to say whether the sea level... All right, you travel with family, you're just begging for interruptions, so that's what happens sometimes. So what you were seeing is changes in sea level, and we can't really tell without studying the regional geology whether the ground was subsiding, making it deeper below sea level, or whether the actual sea level was changing due to glaciation and whatnot. So all we can say is that what you're observing here is stuff deposited at deeper and shallower levels. But from what we can see here, we can't really say whether sea level was changing or whether the ground was rising or lowering here due to various tectonic action. Now the next question is, why are these units all pointing up? The reason this is so dramatic is that all of this bedding is coming up at about a 45-degree angle. Well, we are close to the Himalayan orogeny. We are not in the Himalayas here, but we are Himalaya adjacent. Tectonically speaking, we are close to the Himalayas, and this area has been thrust up during the Himalayan orogeny. That's India slamming into the rest of Asia, and the crust is crumpling up. And that's what we're seeing here, is this is the buckling. These units have all been pushed up at this dramatic angle. If not for the Himalayan orogeny, all of this would be lying flat, and this would all just be flat. I wouldn't say grasslands because I don't think grass could really grow here effectively, but these would all be flat plains. There would be nothing to see here. It would be flat land as far as the eye could see. Now, you also need one other thing to get these nice, beautiful landforms here like this. You need the rocks to be soft enough to be eroded. Not so soft that they're eroded flat, but not so resistant to erosion that they form dramatic, massive mountain peaks. You do get those in other places. If we come over here, we have a look in the distance, let's say over here, you can see that these rocks further back have been pushed up much the same way. In fact, they're even more dramatic. They're almost at a 90-degree angle. They're almost straight up in some places. But those are very resistant rocks. Those are not your soft sands and clays and muds. Those are harder material. It's really far away. I can't tell you what material that's made of, but based on the way it's eroding and very jagged and very high, I'm going to say it's much more resistant than these rocks. So to get these landforms that we see here, you need that tectonic uplift. You need softish rocks. Not so soft that they're eroded flat into a plain, but not so hard that they become massive mountains. You get that perfect combination of stuff along with the interesting colors mixed in from your red hematites, your yellow limonites, your green glauconites, and there is some green out here. I find so far that the pictures online tend to be wildly exaggerated to try to make the barely green grays super duper green. But where you do get green, that is from glauconite mixed in with the sand, often called green sands. The glauconite is an interesting one, and I do hope we see more green material later. But glauconite forms in a very oxygen poor environment, so you can see exactly how much oxygen there was in the water based on the color of the rocks themselves. And in that oxygen poor environment, you get fish poop accumulating, and that's your glauconite. Now there are several other ways that glauconite can form, alteration of clay minerals and one or two other ways. But the more common and certainly the more fun explanation for how they form is the accumulation of fecal waste at depth from various organisms, not just fish, but marine life in general. So while there can be other explanations for how glauconite forms, I always default go to the fish poop just because it's the more fun one. By the way, this is the way photos of this location look when you search them online, but don't buy into the exaggerated hype. This is how it actually looks. Still beautiful, but not cartoonish. I know I've mentioned it before, but there's nothing Chinese people love more than hearing people shout over loudspeakers in natural places. Enjoy the sounds of nature with me. 来，叔叔你过来，给阿姨一个人拍几张看看。你过来吧，给阿姨一个人搞几张看看。啊，对，给你，不用是吧？那就过去。Wait, do I see greens? Let's crank that color up. Fish poop! Sorry, I meant glauconite greensands. So we've learned a lot about how the colors in these layers tell us about the depositional environment, whether it was oxygen poor or oxygen rich, iron poor, iron rich, whether it was deep offshore environment or a more shallow ocean environment. We can see the sea level changes in the layering. We've also talked about how these landforms require uplift through tectonic action, through mountain building nearby. And we've also learned that you can identify how resistant a rock unit is based on whether it serves as a cap rock or whether it's the more easily eroded material underneath. We've learned a lot about geology from these Zhangye Rainbow Mountains in China. Thank you very much for joining me, and I'll see you next time.